second order ordinary differential equations, and I will talk about what they are and why they're called that as we go along. There are three things I want to look at. What are they? What are they used for? And what process do we go through to solve them? That's the main thrust of today. What are the steps we go through to solve these things? They look horrendous, but actually it comes down to just having to follow some steps that can be clearly laid out, and I'll lay them out for you. All you've got to do is to follow those steps. So it ends up in the end being quite a mechanical process to solve these things. So if you want to just make a note of that. We'll start off by looking at an example of where one of these things might turn up. So what we have is a mass on a spring inside a liquid. And this is a good example of where you might come across using one. So it could certainly turn up in some sort of suspension system where you've got a mass on a spring, the mass being the car, the spring being the suspension spring, and some damping going on. So this is a situation, this liquid here is the damping material in here. First thing to do is consider the forces that are acting on this thing. And convention, if we set downwards as being the positive force direction, so therefore up being the negative force direction, we can see that, well, what's the force acting down on this thing? It's the force of the mass pushing down onto the spring, which is here. It's mass. And so force is mass times acceleration. And acceleration is the second differential of displacement, d2x by dt squared. We'll talk about that in a second, where that comes from. A counterbalancing that downward force due to the mass of the thing is the spring, pulling it back up again. That's this. F equals minus kx, which is a formula I'm sure you're familiar with, where k is a spring constant, stiffness of the spring effectively. Okay? So that's acting upwards. And also, if we think about the force, if this mass is moving downwards, there's going to be a force counteracting that movement due to a friction as it's moving through this fluid. Anything moving through air, for example, there's always air resistance associated with it, and that air resistance is always acting against the force, the motion, isn't it? Okay? So if the mass is acting downwards, then there'll be a force upwards counteracting that, the resistance of the fluid, which is given by the viscosity of the fluid, and that's what this symbol here means, the viscosity. This symbol is called eta. And the size of the force depends not only on that constant, which is to do with the viscosity of the liquid, but also the speed. The faster you're moving through it, the greater this friction force. So that's to do with this constant, eta, and the speed. And the speed can be written as a differential, dx, the rate of change of displacement with time. So we have a situation where we can say, okay, at any instance, the force acting on this thing, the gravitational force, is being counterbalanced by the spring constant acting upwards and the viscosity of the fluid acting upwards. So we can write this little equation. So what we have then is the physical model, the thing that we're going to be looking at, the situation. And as will become more important as we look at these differential equations, it's this, it's relating it to the real world that is important in this case. And the assignment you're going to get on this, it's relating it to the real world that I'm more interested in than the maths in a way. Okay? So by looking at this example, we can have a look at that. We've also got some initial conditions. Initially, we'll see that when we look at solving these ordinary differential equations, to get to the final solution, you need to have certain conditions, initial conditions. How is this thing behaving at the start? And there's two conditions we've got here. We know that at the start, at t equal to 0, at the start in other words, it's 3 meters from some arbitrary position that we take to be 0. So we could say the distance from when the spring is completely relaxed and it's not been under tension at all would be our 0. So it's been stretched a distance of 3 meters. Or we could say the position from there, the top where it's attached to here is 3 meters. We've got a choice. It's up to us where we set our 0 to be. So, but initially we're setting that to be 3 meters. And then we're saying at that particular moment in time, the mass is moving at a speed of minus 7 meters per second. So in other words, it's moving upwards in the negative direction. So those are our initial conditions at this moment in time 0. Time 0, we've got those initial conditions. And then we can go ahead, form our differential equation and solve it and come up with a function that describes exactly how this mass is going to behave. That's what we're aiming for. We can plot a graph of how this mass is going to move. What would you imagine this mass is going to do? Yeah, oscillate and then to 0 because of this damping effect. The greater the viscosity of the liquid, the sooner it will drop to 0. Some sort of oscillation maybe, okay? So, yeah. If we go through the differential equation, we end up with this as a solution. And if I were to plot this onto autograph, that's what I'd get, as we predicted. Some sort of oscillation, as Mark suggested, and there it is, that's dying away to 0. So if we look at this graph, time along the bottom here, against x is displacement from our arbitrary start rest position. So we can see immediately that at time 0, it's at 3 meters, which is where we set it to be, didn't we? Okay, so it's starting at 3, and it's moving at, initially, negative 7 meters per second. So the gradient of this curve at that point is minus 7, according to the convention we've set. Well, if we actually look at it, it's a positive gradient, isn't it? But by our convention, we're setting upward to be negative. So, okay? It's moving upwards. You can see that already because the displacement is increasing. Sorry, moving, well, whichever way we set our x to be. Okay? Try typing this into autograph and seeing if you get that solution. So you've got this function up. Let's look at it. On autograph, you notice all sorts of weird things happen to the left of 0 and x becomes negative. We're using this function to model something that's happening in the real world, so we're only ever interested in what happens after time equals 0, positive times in other words. So totally ignore what the mathematics is telling you this function does to the left of the 0. We're not interested in that. Only interested in what happens for positive values of x. That's the first thing to recognize. And then confirm for yourself, please, this start point of 3, which we set our initial condition to be, and that this curve, remember what this curve is showing us, we're plotting x displacement against time. This is time down here. And so the curve is the rate of change of x with time, which is velocity. So this curve at any point going from 0, the gradient on this curve is telling us the velocity. So we can see already that at some point when the gradient drops to 0, the velocity is 0, so that must be maximum displacement. So what is this point? Around about 3.3, 3.4 will give us the maximum displacement of this thing. And then it starts to move again in the other direction, gradually increasing, and then slow its speed, slowing down, and then dying away this oscillation. So you can see how this actually models exactly what will happen to this thing over time, given initial conditions. Okay, so what we're aiming to do is to arrive at a curve like this, which will then tell us, allow us to predict what's going to happen in a given engineering situation and describe the movement of some object. And the point of it is that solving a differential equation is what gets us to this solution. So that's our aim, to end up with a solution like that. And what I'm going to be doing over the next few weeks is how we get to that. Okay. Is to solve non-homogeneous second-order ordinary differential equations. These are ones where the right-hand side is not 0. The general solution to an equation of this form comes in 2 parts. The general solution is formed from the complementary function and the particular integral added onto the end. So we're going to need to look at both of those. The complementary function is a solution to the homogeneous form, so we're going to focus on that first. Lots of awkward words in there, and I'll explain those as we go along, but if you want to make the note. So the terms we have to get used to. I mean, they're newish terms, but it's not anything that's particularly difficult. As I said at the start, it's a case of just learning these steps and moving through them. So what I want to do now is just to introduce you to these steps, and then we're going to look at an example, and within that we'll talk about how it's formed, because where that second differential comes from and all the rest of it, and why they're called second order differential equations and so on. So these steps are the key things that you're going to be performing, and they'll make an awful lot more sense as we go through the example. Solving a second order homogeneous ordinary differential equation. So this might be something that would be worth having to refer to, which will be followed by a table. So these are the steps. 1, form the auxiliary quadratic equation, and we'll talk about that in a second. So that's the first thing you'll do. Excuse me. Secondly, solve that quadratic equation and choose the correct form for the solution. That means look for the right one in the table. Looking at a table of integrals. Once you've got that, given boundary conditions, initial conditions that we had in that example, like at the time equals 0, the displacement was 3 meters and the velocity was minus 7 meters per second. Given the boundary conditions, find the values of the constants. So that's the process, 1, 2, 3. So these are the steps. This is the table of solutions. When you solve your quadratic equation, if you remember back to solving quadratic equations, you get 2 roots to a quadratic equation, 2 answers. Either we get 2 real roots, 2 answers, or we get 1 answer, where in other words the roots are the same, or we get those complex roots. If you remember, if the root turns out to be negative, we have to introduce these complex numbers. So 3 possibilities: real and different, real and the same, or complex. The complex one turns out to be the most interesting one. And for each of these, there's a solution. Y equals some constant a e to the k1x plus b e to the k2x, if the roots are real and different. This solution if the roots are real and the same. And, as I said, this more interesting solution if it's a complex solution. Note, in this complex one, you've got these sine and cosine functions, which is going to give us the oscillation we're interested in. Let's look at an example then. So what we're going to do is to solve this thing. Following those steps, those 3 steps, form the auxiliary quadratic equation, solve it, and choose the correct solution from this table, and then we'll end up with the general solution from which we can try and put in some initial conditions. I haven't given you any initial conditions yet, but we'll look at that when we come to it, okay? Now, first off, this is often time. In fact, in the ones that you're going to be considering, this is likely to be time. So d2y by dt squared, dy by dt. So a note on that first of all. If we've got a graph of displacement against time, s against t, or y against x, we've got here, then you know, don't you, that if I plot a graph at any point, as we sort of indicated already, the gradient is given by ds by dt. And that gradient in a displacement against time curve, the rate of change of displacement with time is the velocity. Stuff we did ages ago when we talked about, first introduced the idea of calculus. Also we have, if I plotted a velocity against time graph, and I got a curve, this time the rate of change of the curve at any given point, the gradient is dv by dt. And the rate of change of velocity with time is the acceleration. So now we can see if we can combine these two together effectively, the acceleration equals the second differential of displacement with time. I differentiate twice. If I differentiate s with t once, I get velocity. Differentiate the velocity, in other words, find the second differential of ds by dt, I've got the acceleration. So that's where that comes from. Okay? So looking at this example again, if this was time down here, if this was time, which it often is, t for time, then this would be an acceleration. So this is often an acceleration. So this is likely to be a mass, because mass times acceleration gives us the force, which is the first example we looked at. So that's the force due to the gravity, this bit. This is a velocity. dx by dt, or dy by dx in this particular example. So this is often a velocity, this bit. So that's going to be our eta, our viscosity. So this bit of the thing is often to do with the damping effect. So this is to do with damping. And finally, this part here, that's displacement. So it's to do with some sort of restoring force, where the force gets bigger directly with the displacement. So therefore, this is going to be some sort of K, some sort of spring constant.
So that was 3 meters when we put the math.
The initial condition was 3 meters, but what we're saying here is that for this part of this equation here, the force due to this part of the equation is due to the spring extending, because the force is proportional to the extension, x. It is, yeah. Well, that's in the example we were looking at, that's true. But of course, what we're going to do is now look at other examples and see what the effect of that being positive is. And when we, yeah. So it might have an effect, exactly. So it's going to have an effect, isn't it? And we'll look at the curve when we've solved it and see what effect that has. So good point, Mark. In fact, you've seen ahead through the problem in a way. And so, yeah, okay. But I just wanted to point out that generally we are trying to relate this equation to a real situation. So I'm not interested, as I said at the start, in can you just solve this? I am interested in can you solve it, but I'm also interested in how does this relate to a given situation, okay? What do these things stand for, these terms? Okay, so let's look at this thing and try and solve it then. So step 1, what was step 1? Form the auxiliary equation. What was the thing again? Okay, so step 1, form the auxiliary equation. That's trivial. Okay? What you do is you let the differential bit be m, which is the symbol that we tend to use in the auxiliary equation. Actually, what letter we use doesn't really matter, but we tend to use m. So in other words, we let this be m squared. So m is the differential, so the second differential is going to be m squared plus 12m minus 8 equals 0. Because there's no differential in the last one, there's no m. So now it looks like a quadratic equation. In other words, we make it look like a quadratic equation by letting the differential be our x effectively. So step 2, solve it. And what equation do we use to solve it? The quadratic equation. So in this case, a, b, and c are given by these. So a is the coefficient of m squared, b is the coefficient of m, and c is the constant. So a equals 4, B equals 12, and C equals minus 8. So solve it. I'll leave you to do that. So solving it, you should get, and there's a solution if you want to look at it, n equals 0.562 or minus 3.562. So that was step 2. Step 3. No, what was step 3? Oh, right, yeah. Oh, okay, sorry, we're not finished step 2 yet, have we? Choose the correct form of solution. My mistake. Messed you up. You did, yeah, you did. Choose a solution. In fact, what we're going to do is we're going to look at step 3, putting the values in next time. So what we do now is look at the table. What we have here is 2 real different solutions. We've got 2 solutions. They're different and they're real. By real, I mean there's no complex part of it. There's no minus in the root. So we look at our table and we see that, therefore, it's the first one. Y equals AE to the K1x plus BE to the K2x. So therefore, Y equals AE to the K1x plus BE to the K2x. Which implies for this one that Y equals AE to the K1, which is 0.562, x plus B e to the minus 3.562x. So for step 3, we need some initial or boundary conditions. What's happening at the start of the time when we're going to model it? Time 0, what's going on with this thing? Is it displaced from its rest position? Is it moving at time 0? Have I given it an initial velocity to get this thing oscillating? If I have initial conditions 0, x equals 0, and velocity equals 0, it's not going to be doing anything. I've got to give it some sort of initial conditions, initial impetus to get it moving. I've either got to displace it so that the springs under tension when I can get it moving, or I've got to give it an initial shove or something, or a combination of the two. So if we say at x equals 0, and remember x is often time, we're going to let y equal 2, so it's initially displaced, and we're going to let dy by dx equal minus 5. So now we've got to try and find those values of a and b. No, just off the top of my head. The differential. So in the initial condition, if this was displacement against time, yeah, so this would be the initial velocity of the thing, which might be 0, but in this particular case it's got a value. So yeah, depending on our convention that we've used. So what was our solution again? The general solution was y equals a e to the 0.562x plus b e to the minus 3.562. Okay, so what we're now saying is I've got 2 unknowns, a and b, and I want to find out what they are. So really I need to set up 2 equations, simultaneous equations, so I can find a and b. So the first condition allows me to set up 1 equation to solve. But the second condition allows me to set up another equation to solve. So I set up 2 equations. The first one's easy enough because it says at t equal to 0, y equals 2. So 1 at x equal to 0, or in this case x equal to 0, y equals 2. So therefore 2 equals a e to the 0 plus b e to the 0, because when x equals 0, the whole thing's 0, isn't it? So that's the first equation, 1. Well, simplified, I suppose, before we write down 1, because e to anything to the power 0 is 1. So therefore, 2 equals a plus b. So that's nice and easy. Once I know a, I can find b easy enough, because a plus b equals 2. So that's the first equation. The second condition that we're given, the second initial condition, is to do with differential. At time equals, sorry, at x equals 0, dy by dx equals minus 5. So we've got to take this and differentiate it to get dy by dx. So for the second one, if y equals a e to the 0.562x plus b e to the minus 3.562x, what's the differential? What's the differential of an exponential function? The 0.562 comes out and goes down, and then the power stays the same, doesn't it, for an exponential? So it becomes 0.562 a e to the 0.562x. What about the next one? Minus 3.562 b e to the minus 3.562x. Now, right, when x equals 0, dy by dx equals minus 5. So when x equals 0, the differential is minus 5. So we can write minus 5 equals 0.562a, because the e to the 0 is 1 again, minus 3.562b. And that's our second of our simultaneous equations. So now we solve these simultaneous equations for a and b. Yeah. Do you remember those days when we were at school and when we started off here? You know, why do we do quadratic equations? Why do we do simultaneous equations? Why do we do algebra? We're using all that now to end up with a model for some engineering situation that will predict exactly how this thing is going to behave in the real world, which is immensely powerful. Can you remember how to solve these? 3 ways. 1, yeah, make them the same, good, so we can eliminate them. 2, substitution, you rearrange 1 to say a equals 2 minus b, for example, and then in the second one, instead of writing a, you write 2 minus b, so we've only got one unknown. Third way, plot them on autograph and look for where they intersect. And as you've got autograph in front of you, you could do that. So type these 2 equations into autograph. You can't put a and b in, it won't recognise them, so use y and x, let a equal x and b equals y, for example, and then type those 2 in and see where those lines cross, and they will give you the values for a and b. Of course, oh yeah, that's right. Plotting these, so a was x, so this is going to give us a, which is about 0.52, roughly, is that right? And b, 1.48. roughly? Of course, this is an approximate solution, and the more you zoom in, the better it will be. So the more exact solution will be to solve it algebraically. But yeah, well, I'll do that maybe next time, Mark. You have a go at it between now and next week, and we'll have a look at it together. But I want to just finish this off. So there's our final general solution with A and B put in. Final thing I want to do on autograph, remember our initial conditions, we set x equal to a value. What I want to do is now put these values for the constants into autograph. So type this into autograph. So instead of A and B now, we know what A and B are. We can actually see how this thing's going to behave. Where is it initially? It should start off initially at time equal to 0, or x equals 0 at 2. So you should find it starts at 2. And then how is it going to behave? Initially it's got a gradient because it's got a velocity. What does it look like? Type this into autograph, we get this. And if we think back to our initial conditions, we said that initially at x equal to 0, the displacement was 2. So that agrees with this, x equals 0. And also, there is a gradient. So that means there is an initial rate of change of y with x, or velocity if we were doing displacement against time. So if you were to zoom in on this in autograph and find the gradients of the line at that point, you would find it would be 5, which we set it to be, minus 5 in fact. Okay? So here dy by dx equals minus 5. So we've got the initial conditions on the curve, and then we can see how it's going to behave as x increases. Next time we'll look at couple more examples and then move on to the next stage. Okay?